All right, so I think some of you were maybe a little caught off guard by the assignments that were due yesterday. Um, and so I wanted to kind of go over some of the equations that you saw there. And it requires, all of those questions require a lot of algebra. Um, it, basically, anything we're doing in those types of questions where you're finding extrema or finding where the function is increasing or decreasing or concave up or concave down, any of that requires the same basic process of taking the derivative and finding where it's undefined or equal to 0, or the second derivative if you're talking about concavity, finding it's where it is 0 or undefined, and finding where your inflection points. All of that takes some algebra. And so I wanted to go over, I think, a little bit of the algebra that was throwing you off. In particular, this not only does it take algebra here, but it takes some trigonometry. So if you weren't quite sure how to solve some of these trig equations, hopefully this will help. So I have here one of your questions. The ones you had in your homework, either you had one either that looked like this, or maybe it was this exact one, but you should have had at least something similar on your homework. So you've got this function, you take the derivative of it. I'm not going to go into the derivative here, it's just a basic chain rule. The derivative of cosine is negative sine, but then you multiply by the derivative of the inside. The derivative of sine is cosine, then you multiply by the derivative of the inside, so it's just some chain rule. And anytime you take the derivative to find any of the interesting things about the function, again, increasing or decreasing, first derivative test, whatever it may be, one of your very first steps is to find your critical numbers. So your critical numbers, you want to check, are there any places where your derivative is undefined? Are there any places where the derivative equals 0? Now, the derivative, first of all, I mean, sine and cosine, those functions work everywhere. Their domain is all real numbers. There's nothing weird where you might be dividing by 0 or taking square roots of negatives or logarithms. None of those things that could mess up your domain are happening here. This is just a regular old sine function and cosine function that works everywhere. So we don't get anything from this. But the other thing we have to check is where the derivative equals 0. And this is where we need not only some algebra, but some trig skills. So let's find out where our derivative equals 0. So negative 6 root 3 sine of 6x. And I'll say that none of this is new for y'all. It's just maybe, I don't know, maybe it's been a while since you've had to do something like this, and maybe you've forgotten. We did start at the beginning of the semester. I did a short trig review, but even that was a few months ago, so maybe you've forgotten some of those things. But we're trying to find out where our derivative is equal to 0. And before I go into solving this, let me show you real quick the unit circle. I have it on this other page. And I just filled in the first quadrant, but if we have the first quadrant figured out, we can figure out anything else we need. And let me just show you an example of a really basic trig equation. On the other page, we have one that's slightly more involved, but let's do just a really basic trig equation. If I say that sine of theta is 1/2, then what are all of your possible solutions for theta? Well, to answer that, we have to know how the sine function works with the unit circle. The sine function takes the y values from the points on the unit circle. So all I have to do is I have to know my unit circle well enough to know where I have y values of 1/2. So that would happen here at pi over 6. So theta could be pi over 6. But then if I'm looking at my y value of 1/2, if I go straight across over here, that y value is also 1/2. All right, so I need to think about what angle that is. That is 1 or pi over 6 away from pi radians. So that would be 5 pi over 6. And so this point at 5 pi over 6, we've got this point negative root 3 over 2, 1/2. The y value here is 1/2. So 5 pi over 6 would also be a solution. And we know from our trig classes that the sine function is periodic. If we just keep going around the unit circle more times, we keep getting more answers. So pi over 6, 5 pi over 6, I could go around an extra rotation. Here's 2 pi, that's 12 pi over 6. So then this would be 13 pi over 6. Let's see, 13, 14, 15, 16, 17 pi over 6. And you can keep going, just keep adding multiples of 2 pi, or we can go in the clockwise direction and subtract multiples of 2 pi, right? So there's infinitely many solutions to this equation. Here's just 4 of the solutions. Okay, so this is kind of the most basic version of a trig equation, and when you're doing your homework, your trig equations are going to eventually turn into something like this, okay? Where you can basically just, if you know the unit circle, answer based on knowing the unit circle, okay? One more quick example. If I say tangent of theta is root 3 over 3. Now, if you like, you could pause here and try to figure this out on your own. Figure out some angle where this works. So one of the solutions is pi over 6. And you can double check that. If I do tangent of pi over 6, let's make sure we understand why pi over 6 is one of our solutions. Well, remember what our tangent function does is it takes the y value divided by the x value. And at pi over 6, if I do y divided by x, I have 1/2 divided by root 3 over 2, which is the same thing as 1 over root 3. The 2's would cancel. And then if you rationalize your denominator, that's root 3 over 3. So pi over 6 is a solution to this equation. And now for the tangent function, we're doing the ratio y divided by x. So we need to think about where's the next angle where this could happen. Well, obviously if you do an extra full rotation, you get another answer. So like we said a second ago, yes, 13 pi over 6 would be an answer. But there's another place on the unit circle where y divided by x would give us this same answer of root 3 over 3. And that would be with the tangent function. If we go over to the opposite quadrant, we get the opposite point. So this point here would be negative root 3 over 2, negative 1/2. And if I do y divided by x, then I'm going to get my same answer because the negatives will cancel, right? Negative divided by negative is still positive, so I'd still get a positive root 3 over 3 for my answer. So I just need to know what angle this is. So this is just kind of counting my way around the unit circle. I've got starting here at 5 pi over 6, 6 pi over 6. This is 7 pi over 6. Okay, so pi over 6 is an answer. 7 pi over 6 is an answer. And again, any full rotation away from 7 pi over 6 would be an answer. So if I go 7 pi over 6, a full rotation, let's see, that's 12 pi over 6, 13 pi over 6, 13, 14, 15, 16, 17, 18, 19 pi over 6 would be another answer. So I could keep going around the unit circle as many times as I like and getting more answers. All right, so understanding how to solve these basic trig equations make a big difference in solving the ones you have to do for your homework. Okay, so let me go back to the other page now and let's solve that equation. Your goal with an equation like this, when you're setting your derivative equal to 0 and solving, if your equation involves trig, your goal is to eventually figure out some way to make it look like one of these equations we were just talking about, this type of equation where you have some trig function equal to some number. If I have some trig function equal to some number, then ideally this number is something I can pick off of the unit circle and then figure out the angles. Okay, so that's what we're looking for. If I'm solving this equation, the way I can get there is I've got two different trig functions, sine and cosine. Ideally, I would just have one trig function showing up. So here's what I can do. First of all, let's just move one of these trig functions over to the other side of the equation. I can add a 6 root 3 sine of 6x to both sides. There's other approaches we could take, but I'm just going to get this to where I have these different functions on either side. So I've got a 6 cosine of 6x equals 6 root 3 sine of 6x. I could have moved the cosine to the other side. I just chose the sine just so I have a bunch of positive stuff instead of negatives. Notice both of these have a 6 in them. I can go ahead and get rid of those. If I divide both sides by 6, then those are out of the way. I don't have to worry about those 6's. So then I have cosine of 6x equals, I had root 3 sine of 6x. I forgot about the root 3. Equals root 3 sine of 6x. Now, what I would do next here is, let's look at what happens if I divide both sides by cosine. Cosine of 6x. So the reason I'm doing this is because it's going to allow me to get things down to just one trig function instead of two. So on the left-hand side, cosine of 6x over cosine of 6x is 1. Now, what's sine of 6x divided by cosine of 6x? Well, sine over cosine is tangent, so I have root 3 tangent of 6x. All right, so again, the nice thing about this is I just have one trig function showing up now instead of two. So this will be easier to solve. It's closer to having that format that I want, where I have some trig function equal to some number. Now, if I just move this root 3 over to the other side, I have tangent of 6x equals 1 over root 3. And if I rationalize the denominator here, this is actually going to look a lot like the equation we had on the previous, or on the other page. this would be tangent of 6x equals root 3 over 3. Okay, now look at how this equation, this equation here, look at how, I'm not done solving it yet, but look at how it compares to this equation over here. Tangent of theta equals root 3 over 3. What we're solving is tangent of 6x equals root 3 over 3. Okay? So the angle that I'm looking at, this is basically, if I say that theta is the same thing as 6x, just to make this look cleaner, then I can say tangent of theta equals root 3 over 3. And we already solved this equation, right? Tangent of theta equals root 3 over 3. We found that theta equals, there's a whole long list of numbers we could write down. We could write down pi over 6, 7 pi over 6, 13 pi over 6, and so on. The list goes on forever. Just keep adding multiples of pi and you get more answers. All right, so this kind of describes all of the solutions to this equation, except I solved for theta. Really, we're trying to solve for x, right? But theta is 6x. So 6x equals all these things. So then if 6x equals all these angles, then finally the last step here is we'll divide by 6 and you get all of your x values. So finally we get x equals, if I'm dividing everything by 6, I could have pi over 36, 7 pi over 36, 13 pi over 36, 19 pi over 36, and so on. The list goes on. Again, just in this case, since it's the tangent function, these are all just adding multiples of pi to that original answer, pi over 6. So I've got this whole list of infinitely many answers. So this function by itself has infinitely many critical numbers, infinitely many places where the derivative equals 0. In other words, it has infinitely many places where the function flattens out, where you could maybe have a max or a min, where the function may be changing directions between increasing and decreasing. Okay, a whole lot of ways to say the same thing. But these critical numbers, in your homework, they give you a specific range or a domain to look at. If they tell you that they want x values, specifically x values greater than or equal to 0, less than or equal to pi over 3, for example, if they give you this interval to deal with, then you don't need all of the infinitely many answers down here. You only pick the ones that are bigger than 0 and less than or equal to pi over 3. Okay, well, so my critical numbers, pi over 36, yeah, that's bigger than 0 and it's smaller than pi over 3, so there's one of them. 7 pi over 36, yes, that's bigger than 0, and it's still less than a third of pi, so 7 pi over 6 would be another one. Or 7 pi over 36. 13 pi over 36, if you think about 13 over 36, that is bigger than pi over 3, or 1/3. 13 over 36 is bigger than 1/3, so this is bigger than pi over 3. All right, so really just these two x values are the ones that are my critical numbers inside of my interval. All right, so if they don't give us an interval to work with, then we have to describe all of the critical numbers. There's infinitely many of them. But if they give you some interval to work with, then just pick the ones that are inside that interval. All right, so we've only got 2 critical numbers inside this closed interval. One thing to keep in mind, if you're working inside of a closed interval, go back to what we talked about in section 4.1. If you're wanting to find your absolute extrema could either happen at the critical numbers or at the endpoints. Okay, so if you have a question about absolute extrema, we've talked about how to do that in 4.1. You need to check what's happening at your critical numbers and at your endpoints. Okay, so this is all stuff that you've seen before, and I know it's stuff that maybe it's been a while since you've had to do this, or you're a little rusty on it, and that's fine. Hopefully after you do this a few times, though, you start to get the hang of it. And in fact, if you do this same question and have to do it for y double prime, it's the same basic process. Take the derivative of this derivative, get y double prime, and solving that equation will be a very similar process to what we did here. And again, you'll eventually get one of these basic equations that we know how to solve if we know our unit circle. Some trig function equal to some number, and then you pick off the appropriate angles from your unit circle. All right. So hopefully that helps. For those of you who are struggling, I know some people were struggling with the algebra and the trig functions on that homework. Hopefully this helps clear some of that up.